So my first example here is our friend, the geometric series, which you see behind me. What I wanted to show you guys is what happens when you actually look at the partial sums and start setting up the terms, adding up the terms. So let me see if I can get this to work. Yeah. There we go. Perhaps. You'll see that. I hope you see that. So what we have is this is the function we're looking for, 1 over 1 minus x. And as we know from the series behind us, we only care about the values where the series converges, which is between -1 and 1. So obviously, myself here, I'm not sure how that works, but obviously this guy has an asymptote at x equals 1, so we can see it's going up a little far here. Okay, so now if I take, you know what, the first one is just 1, so that's not very interesting. So I took, the partial sum S1, which would be 1 plus x. All right, that's that line. You see, it's close. It's a close approximation, only very close to the point x equals 0. Pretty much, that's not a great approximation, right? So if I add another term to my partial sums, it looks a little better, right? I'm getting a little bit closer to my green. Now, so I added 5 terms, and you can see it's pretty close. I can still see the green up here, but close between, more or less between a -0.5 and 0.5. This gives us a really good approximation. Now I did 10 terms just so you can see. By 10 terms, I'm pretty close. You can't even see the green until out here, right? And here. So you can see as you add more and more terms, visually speaking, you're going to get closer and closer to the green curve for more of the distance there, for more of the distance between -1 and 1. Now, the question is how many terms you need. It's going to depend on your application. Oftentimes in physics, it's good enough just to have a couple terms, because if you're, see if I'm, I don't want to get rid of it, but okay, fine. I want to do that. You see, if you're really close here, if you're just really right around that point, even the linearity, even the linear one would be good enough. Okay. Now, my second example is going to be sine of x. Okay. Sine of x, if we look at the Taylor series approximation, well, this is actually the Maclaurin series, because it's the Taylor series around x equals 0. So this is what that looks like. I'm not going to write up the nth term formula, but this is sine of x, and around x equals 0. So if I do just one term of that, in fact, right around x equals 0, that's pretty good, right? If I start adding some more terms, what happens is I add more terms. Notice these, I'm getting closer and closer and closer. I'm getting closer, further out. So even by 3 terms of my Taylor series, I'm starting to get that nice, that first hump there. And so I keep adding them, and I did here up to 5. So you can see the 5th one, let me get rid of these so you can see that final approximation that I graphed is actually really close. I've got the whole first period there, and even further out, it's looking really good. Okay, I want to be sure that you guys understand what we're looking at here is the partial sum. So it's not just the 9. It's not just x to the 9 over 9. If I graph x to the 9 over 9 factorial, okay, That's what 9. Let me do it here. 9 factorial. Look, that's useless, right? That's now this green one, that looks nothing like the sign. So it's not the nth term that we're graphing, but the nth partial sum. There we go. I don't see, I don't want to see that. Okay, now what's interesting here, I said this is the Maclaurin series, right? So the Maclaurin series is the Taylor series around x equals 0. Now I can also do an expansion around another point, A. And in our lecture about Taylor series, we did, I think, cosine around pi over 3. But because I have, your book has sine around pi over 3, so I'm going to write this up. It turns out, you know what? The nth term formula is awful looking, but let's see, it would be minus root 3 over 2, times 2 factorial. Forget that, it does not work. Okay, so this is kind of looking more weird. Yes, I got my 3 factorial here. But rather than being expanded in terms of x to the power n, now I've expanded 2 times 4 factorial. Sorry guys, I apparently can't write and speak at the same time today. That's not good. All right, so I'm not sure if you guys can see that, but we're like that. Okay, so this is also sine x. This is also a Taylor series expansion for sine x. It's not for sine x minus pi over 3. It's sine x. It's just that it's in terms of powers of x minus pi over 3 instead of being in terms of powers of x. And so the question is, like, why would you want to do that? Well, as you saw over here for the Maclaurin series, where we're expanding around x equals 0, this one is starts out even with a few terms, very good approximation around x equals 0. Now, if instead I look at this mess, okay, it's not a very good approximation at x equals 0. Look at the first term. It's like way off. It's an approximation, this approximation is good around x equals pi over 3, okay? So here's x equal pi over 3, and as I add another term, I'm getting my good approximation around the point which is the middle here, right? And so that's why it's called expanded around that A, which here is pi over 3. And I don't know, the colors are wacky here. It didn't give me a green. Oh, there, it got me a green. Okay, so it's now after, this is 4 terms, I think. One, yeah, I think this one goes out to, it's hard to see. Okay, this is to 4. Okay, my biggest one was to 4. I'll get rid of these guys so it's easier to tell. So that's not bad. It's not as good as, you know, here. It's still pretty good here, but it took me 4 terms to get this much. But around this point, this is super good, right? So if you were doing a problem that was where you needed to approximate around a point that was not 0, you might want to choose to use this instead, or let's see if I do 2 terms here, right? If I have 2 terms here, that's really good here. If I look at my other one, technical difficulties. If I look at my other one with 2 terms, it's not so good at pi over 3, right? So I may want to use the other one. So it just really depends on what your application is, where you're using this. For the most part, these are the most common, the ones around x equals 0. That's why most of our problems that we're going to do will use the Maclaurin series, because you simply do end up using them more often, but sometimes you do need the other one as well. So